Okay, another example of finding where a function is increasing and decreasing using the derivative. So this is number 7 in the book. The graph of the function's right there, so you can look at the graph and kind of verify after the fact, what we have found is right. But again, the goal here is to look at the formula of the function and then make an assertion about what happens on the graph. So, the fact that the graph is sitting there in the book is meant to kind of help you check your answer. Okay, but how do we find where a function is increasing and decreasing? Okay, well, there's a set of steps in the book. First thing they tell us to do, of course, is find the derivative of a function. Okay. Again, this function's not too bad, so the derivative we can find pretty easily. It's 4x cubed minus 4x. Okay, I'm just using the power rule and some of the basic rules of derivatives there to get the derivative. Okay, now the next thing they ask us to do to figure out where this function's increasing and decreasing, it's an involved process, but to do this systematically, now that we have the derivative, we want to find those critical numbers. Okay, critical numbers are where the derivative is either 0 or undefined. So now that you have that derivative, that's sort of the first step. The second step is you have to answer 2 questions. Where, if anywhere, is the derivative equal to 0? And where, if anywhere, is the derivative undefined? Okay, because if either of those 2 things happen at a particular value of x, that's where our function can change from increasing to decreasing or decreasing to increasing. Okay, so let's talk about these 2 things. Do either of these ever happen? Okay, well, let's get rid of this one right away. Is this derivative ever undefined? The answer is no. A derivative is only going to be undefined for values of x that make us divide by 0 or something like that. And of course, there's no division here, so this derivative is never going to be undefined. Okay, but is it ever equal to 0? Well, probably, but the only way to figure that out is to check by hand. So we set up the equation. We take the derivative itself, 4x cubed minus 4x, and set it equal to 0. So we'd like to solve this equation for x. Now in the book, on some of these problems, the equations can be a little complicated. This is a polynomial equation, but this one can be factored pretty easily. Okay, I can factor x out of the left side. In fact, I can factor 4x out, so let's go and do that. 4x, and that'll leave me x squared minus 1. Okay. Well, in fact, I can factor further, right? This is 4x. Okay. X squared minus 1 factors as x minus 1 times x plus 1. Okay. So since the left side is factored and the right side is 0, I know that this equation is going to be true when any of these factors are equal to 0. Okay. So if I set 4x equal to 0, I'll get one solution, right? If 4x is equal to 0, x has to be 0. If x minus 1 is 0, x would have to be 1. And if x plus 1 was 0, x would have to be negative 1. Okay. So these 3 numbers are what the book calls critical numbers. Okay. Now, what we have to do next is take these 3 critical numbers and divide the set of all numbers into, in this case, 4 intervals. Okay, so let me back up here. Probably go ahead and erase this. So this derivative that we found is equal to 0 at exactly 3 numbers. Okay, so these are our critical numbers. Okay. Now the theory in the book is this: our function can only change from increasing to decreasing at these 3 points. Okay. So, for example, what does that mean? Well, if you look at the numbers in order, they're negative 1, and then 0, and then 1. So that actually gives us 4 intervals. Okay. So what are these intervals we need to test? And now we're really getting into the 3rd step here. We need to find these test intervals. Okay. Well, there's going to be 4 of them. We need to test everything to the left of negative 1. We need to test everything between negative 1 and 0, everything between 0 and 1, and everything from 1 to infinity. Okay. Okay, why? Why those intervals? Well, these are the 4 intervals that are determined by those 3 critical numbers. Okay. So the function's not going to be increasing or decreasing at these 3 points. But for example, the first critical number is negative 1. So everywhere to the left of negative 1, it can only be increasing or it can only be decreasing. It can't change. So it only does one thing, increase or decrease on this interval. Okay. So how do we do that? Well, we need to get a test. We basically need to test f prime of x for each of these intervals. Okay. So here's the derivative. I need to pick a number in each of these intervals and plug it into the derivative and see what I get. Okay. So for instance, negative infinity to negative 1. Well, negative 2 is in that interval. Okay, so what do I get when I put negative 2 into the derivative here? Well, let's see if I'm careful. I can probably do this one in my head. It's going to be, let's see, negative 32, it'll be plus 8, so it'll be negative 24, which is less than 0. Okay. So on this interval, the derivative has to be negative everywhere. Okay, it can't change until negative 1. So everywhere to the left of negative 1, the derivative is negative. That means the function is going to be decreasing on this interval. Okay. Now, between negative 1 and 0, those are our next two critical numbers. Okay. Negative 1 is the first, and then we have another one at 0. In this interval, the function can only be doing one thing. So we have to test the derivative at some number between negative 1 and 0. Okay, now remember, these are intervals. Okay, so they're not points, they're intervals. So these numbers, from negative 1 to 0, those x values, our function is either increasing or decreasing. Okay, well, this one's a little tougher, because we can't pick a whole number in this interval. Okay, we have to pick something between 0 and negative 1. So negative a half will work. Okay. Well, again, not the best number, but I think if you put negative 1/2 in here, let's see, what are we going to get? We're going to get be negative 4/8, so negative 1/2 plus 2 should be something like 3/2, okay, which is positive. Okay, so that tells us on this interval the function is increasing. Okay. Now the next interval, what are we going to pick to test into the derivative? Because we need to figure out what the sign of the derivative is. Well, probably 1/2. Okay. Well, if you put 1/2 in for x, you get negative 3/2 for the derivative. So again, the derivative is now negative. That means the function is decreasing for x values between 0 and 1. Okay. And then finally, we got to put in a number that's bigger than 1 into our derivative. I'd probably try something like 2. It's a nice number. And again, when we put 2 in here, I think we're going to get positive 24, which is greater than 0. So now the function is increasing. Okay. So 4 intervals, okay, everything to the left of negative 1, okay, the x-coordinates from negative infinity to negative 1, our function's decreasing. Then when x is between negative 1 and 0, the function's increasing. Okay. And then when x is between 0 and 1, it's decreasing again. And finally, past 1, it's increasing. If you look on the graph, you'll see that's exactly what happens. So we can figure out where it's going to be increasing and decreasing first, and then check that on the graph.